We noted in the previous video that the rates of many chemical reactions depend on the concentration of the reactants. In this video, we look at the relationship between reactant concentration and time and introduce the concept of integrated rate laws. Now, if we consider the simplest form of a generalized chemical reaction in which a single reactant A is converted to a single product B, we can write the generalized form of the rate law like this, where the rate equals the rate constant K times the concentration of the reactant A raised to a power M. If the reaction happens to be first order, then the value of the exponent M is equal to 1, and the rate law is simply written as rate equals K times the concentration of A. If the reaction happens to be second order, then the value of the exponent M is equal to 2, and the rate law is written as rate equals K times the concentration of A squared. And if the reaction happens to be a zero order reaction, then the value of the exponent M is equal to 0, and the rate law is written as rate equals K times the concentration of A raised to the power of 0, which simply equates to rate equals K, the rate constant. Now, what rate laws actually do is show how the rates of reaction are related to the concentration of reactants. And while this is very important in many industrial, environmental, and biomedical applications, it's also just as important to be able to predict the concentration of a reactant or a product at any time during a chemical reaction. So an integrated rate law will allow us to do this. And an integrated rate law is a relationship that expresses the concentration of a reactant as a function of time. Now, in this reaction of A going to B, it implies that as the reaction proceeds, A is being consumed and B is being produced, and we can plot the course of that reaction using a concentration time plot, where we see that as A is consumed, its concentration decreases with time, and as B is produced, its concentration increases with time. Now, you may recall from an earlier video that the rate of reaction can be determined from the slope of these curves at any point during the reaction, and this is known as the instantaneous rate and is determined by calculating the slope of the tangent by considering the change in the concentration divided by the change in time. So the instantaneous rate at any time during the reaction can be expressed as minus the change in the concentration of the reactant A divided by the change in time. And remember, the negative sign is there because we are talking about the rate of disappearance of a reactant, and we need to ensure we have a positive value for the rate of reaction. So what we have now are two ways of expressing the rate in terms of the concentration of the reactant, and both expressions are equally valid ways of expressing the rate. And because these two expressions are both equal to the rate of reaction, we can equate the terms on the right-hand side. If the reaction happens to be first order with respect to A, then the right-hand side of this new expression will simply be K times the concentration of A. If the reaction happens to be second order with respect to A, then the right-hand side of this new expression will be K times the concentration of A squared. And if the reaction happens to be zero order with respect to A, then the right-hand side of this new expression will be just the rate constant K. So what we'll do now is consider all three cases one at a time. And we'll start with the first order case, where the right-hand side of the equation is equal to the rate constant K times the concentration of A. Now we can rearrange this equation and do a little calculus involving the integration of the function within limits to achieve this relationship here, which is known as the first order integrated rate law equation. Now, while the mathematical derivation of this expression is not too complicated, in chemistry, the ability to understand and apply this equation is far more important than the knowledge of its mathematical derivation. And so it's important to understand exactly what each term means in this equation. So the AT term refers to the concentration of A at any time T during the reaction. The A0 term refers to the concentration of the reactant A at the start of the reaction, that is, at time T equals 0. K refers to the rate constant, in this case, more specifically, the first order rate constant, and has units of seconds to the -1. And finally, T refers to the time interval of the reaction. So this equation therefore reads as the natural log of the concentration of the reactant A at any time during the reaction is equal to minus Kt plus the natural log of the initial reactant concentration. And this means we should be able to calculate the concentration of reactant at any time during the reaction, so long as we know certain key experimental factors such as the time of reaction, the value of the reaction rate, the value of the rate constant, and the initial concentration of the reactant. Now it turns out that this equation has the general form of a straight line y equals mx plus b, where in the case of our integrated rate law, the ln AT term is equivalent to the y variable, time is equivalent to the x variable, the negative of the rate constant is equal to the slope of the straight line, and the ln A0 term is equivalent to the y-intercept. And so while we see that for a first order rate process the concentration of the reactant A will decrease exponentially with time, if we were to plot the natural log of the concentration of the reactant A versus time, we would see a straight line relationship with a slope of minus k and a y-intercept equal to the natural log of the starting concentration of A. Now, a slightly rearranged form of the first order rate law equation, where the equation is expressed in terms of the ratio of starting concentration and final concentration, will often be useful. However, both forms of the equation can be used to do some very useful calculations. For example, if we know the initial concentration of reactant and we know the final concentration of a reactant after a time period t, then the only unknown in this equation is the rate constant k, which can be readily calculated. If, on the other hand, we know the rate constant k and we know the concentration that we started with, then after a certain time period t, we should be able to calculate the concentration of reactant that is remaining after that time period. Again, a very useful thing to be able to do in real-world applications. And it doesn't matter which version of these two equations you use, since they are rearranged versions of each other and are mathematically equivalent. You may just find that at times the bottom version becomes more useful in certain situations. Now, for a second order reaction, the rate of reaction is equal to K times the concentration of A squared. And again, we can rearrange this whole equation and do a little calculus involving integration to achieve this relationship here, which is known as the second order integrated rate law equation. Again, in chemistry, the mathematical derivation of this expression is less important than the ability to understand and apply this equation. The terms in this equation have the same meaning as in the previous example, except that the rate constant K in this case is known as the second order rate constant and has units of molarity to the -1, seconds to the -1, or litres per mole per second. Like the first order rate equation, the second order rate equation also has the form of a straight line equation where the 1 over AT term is equivalent to the y variable, time again is equivalent to the x variable, the k, the value of the rate constant, is equal to the slope, and the 1 over the starting concentration of the reactant A is equal to the y-intercept. So in a second order reaction, the concentration of reactant will decrease in an exponential-like manner, similar to the first order case, but the biggest difference is that the decay towards zero is slower in the second order case. Nevertheless, if instead of plotting concentration versus time, we were to plot 1 over the concentration versus time, we would see a straight line relationship with a positive slope and the magnitude of that slope being equal to the rate constant k. In this case, the y-intercept would be equal to 1 over the starting concentration of A. For a zero order reaction, the rate of reaction is constant, so the right hand side of this equation simply becomes the rate constant K, and again we can arrange this equation or rearrange this equation and do a little calculus involving integration to achieve this relationship here, which is known as the zeroth order integrated rate law equation. The terms in this equation have the same meaning as previously, except again that the rate constant in this particular example is talking about the zero order rate constant, which has units of molarity per second or moles per litre per second. Like in the previous cases, the zeroth order rate equation also has the form of a straight line equation where the AT term is equivalent to the y variable, time is again equivalent to the x variable, the negative of the rate constant K is equivalent to the slope of the line, and the A0 term equivalent to the y-intercept. In a zero-order reaction, the concentration of a reactant will decrease linearly with time, which is quite different to the other cases, and this linear decrease is consistent with a rate of reaction that is constant. So in this case, a plot of reactant concentration versus time is the defining plot to look at, and we see that the slope of this line is equal to minus K, and that the y-intercept is equal to A0. Now this table here summarises all of the important relationships for the integrated rate laws, which relate the concentration of a reactant to time during the course of a reaction. The table considers the case for reactants that conform to zero, first or second order kinetics, and shows the equation for the rate laws in each case. It shows the units for the rate constant in each case. It shows various forms of the integrated rate laws for each case, and it shows the straight line graph information to be used in each scenario. The table also refers to the mathematical expressions for the half-life of chemical reactions, which we will consider in more detail in a subsequent video.